Welcome to another part of the ISM course in Statistics 1, this time with a unit on linear regression, and in particular determining the coefficients of a regression line and calculating the R-squared coefficient of determination. Let's jump right into it. When we start, we have one main goal with linear regression. This can be formulated as follows. We have a dependent variable, and we want to explain this dependent variable y via one or more independent variables x. Here in this case, we only consider the situation where we only have one single independent variable. And the goal lies in fitting a function, a line. This is linear regression, so we consider only lines. And fitting a line to the scatter plot of all observed values, whereby the quadratic distances between points and function are minimized. In particular, this last part we will take a look in a moment at. Before we do this, first some of the requirements that needs to be met. First off, the independent variable influences the dependent one and not vice versa. So there needs to be a clear-cut causal effect from x on y. Then the variable x is exogenous and not stochastic, so it's given from the outside, is not determined via the model, and it's not a random variable. The variable x is not correlated with the residuals, meaning x only influences y, more or less in a different way. The residuals epsilon I are normally distributed with a mean of 0. This is a central requirement for linear regression. In particular, if later on we want to do any tests, all of those tests won't work in any which way when we do not have this requirement, and we also cannot be assured that the coefficients we determine are actually the best fit if this one is not met. Then the residuals have a constant variance. We do not have any kind of heteroscedasticity. The residuals are not pairwise correlated with each other, so we do not have any type of autocorrelation, neither serial nor spatial. Well, that's basically all the important stuff. So how are we going to get our coefficients for our regression line? Well, we start with the above mentioned scatter plot. We just take a look at the different combinations of x and y, and our goal is to fit a line which matches as good as possible those data points. For this, we consider the distance of all the points to the line. That's, for example, this one for the one above, this one for the one down here. The problem, if we take this type of distance, is, well, if we just take the difference, we would have positive and negative values and would cancel each other out. So we cannot do it like this. However, we can consider the absolute. If we do this, however, we will have a problem because the absolute as a function brings with it some problems when considering deriving this function. So this is also not a good choice, but what we can do is we can square this distance. This has two big advantages. The first advantage, well, if we square the distance and we consider the distance here as something which might change from the function, which would be something like x to the power of 2, it's relatively easy to get the first derivative. So it's easy to handle in achieving our goal, first advantage. Second advantage, if we square this, this will only make small deviations from the line become even smaller, but large deviations from the line will become even larger. So by using the squared versions, we try to find a line which leads to a lot of small deviations, but tries to avoid large deviations. This is like an added bonus on all of this. Okay, how can we get this in a more formalized version? Here again for the other point. We consider the y-coordinate of this data point, and we consider the corresponding y-coordinate from the line. This is the yi with a hat. The yi with a hat can be determined by inserting the xi into our regression line. Okay, then we have the distance. We square the distance, so it's basically yi minus yi hat, in parentheses, to the power of 2. And we do this for all the data points. Then we just sum up all those square differences and minimize this function. Okay, but minimize for what? Okay, for this, let's just take one step back and do all the stuff I just mentioned, but in mathematical terms. So we're going here. We first get the difference between observed values and estimated values. This one is squared and summed up for all the different data points. Then we just replace our estimated values, so the values for the regression line, by inserting xi into our theoretical regression line, which is a plus b times xi. A being the hypothetical y-axis part, so the intercept, b being the slope of the hypothetical regression line. Okay, if we have this, we basically have a function where we know all yi's, all xi's, and we only have two variables or two parameters which we do not know, the a and the b. And we want to find a solution which actually leads to the least distances, so which minimizes this expression. So we can consider this as a function of a and b, and then try to find a minima with regards to a and b, which basically would suffice for a solution to our problem. So first off, we make this a little bit easier by factoring out. Then we take our first derivative of this expression with regards to b and with regards to a. This leads to the following two expressions. Well, if we have those two first derivatives, to find an extremum, to find a minima, we have to equalize them with 0, which would then look like this. This is already, well, simplified a little bit. Both of the equations are divided by 2. So we have this, and then we can just reformulate this a little. So we divide the second equation by n, bring a to the right side, so it looks like this. Then we already see the first term. This is more or less the average, the mean of y, and the second part is more or less the average of x. So we can simplify this to read as mean of y minus b times mean of x equals a. So this was one of our two equations. The other one would look like this. But here as well, we can simplify a little bit. The first part, we have more or less the mean of x times y. Then we have this part which we just replaced for a. Then we have the mean for x. Then we have the mean for x squared. So if we just reformulate this and solve for b, this would look like the following formula. The first part for b actually looks rather strange, but if we also simplify this a bit, this becomes quite familiar. So on the part above the fraction line, we have the covariance of x and y, and we divide this by the variance of x. And that's also what's the last part, with covariance divided by variance of x. This gives our regression slope, and as defined above, we have the mean of y minus b times the mean of x, giving us the intercept for our regression line. So in this case, we just determined our two coefficients. So this was relatively easy. We just went steps by step. Okay, we could have done some in-between steps for the deduction, but in the end what matters are those two formulas for A and B. And if we have our regression line, here again summarized for those two formulas, we can go on and get an idea how good this estimation, those parameters, this line actually is. And for this, we return to our example, the scatter plot, the line we have, and we concern ourselves with the so-called coefficient of determination. And what this does is basically compare, if we wouldn't know anything, the best guess for y would be the mean of y. However, here we have additional information, all the information which is present in x, in the regression line. So we estimate in how far the regression line provides better results than just taking the mean of y. And we do it by first considering the total variance. The total variance, as we mentioned in some earlier sets, is the squared distance of the data point towards its mean. So here is the distance from the data point to the mean squared. This is the total variance. However, the part which is covered from the mean towards the data point, that's a part which is already explained via the regression line. And the coefficient of determination basically compares those two values. It goes about and just divides explained variance of y by total variance of y. Well, here that's the unexplained variance. So what we can do, if we have those two additional values, we see what our coefficient of determination, our R squared, actually is. That's the difference, the squared difference of the mean of y and the estimated value, the yi hat, divided by yi minus the mean of y squared. And we do this not only for this one data point, but again we sum this up for all our data points. And this would lead to this following formula: the explained variance, as described above, divided by the total variance. And this then is our R squared. Again, we have this here in the different version, the nicer version. And we can also say this is nothing else than basically the variance of the estimated y divided by the variance of y. Okay, what do we know about this R squared? We know that it always takes values between 0 and 1, meaning if we have a value of 0, we can explain nothing of our variance of y. So considering the mean is as good as considering any kind of regression line. So this is the worst result possible. The best result would be 1, so we have a perfect fit on all data points. So we have basically a straight line through all the data points. Well, this sounds familiar. This is basically a similar version than our correlation coefficient being -1 or +1. And this is why this is called R squared. Because if we have a simple linear regression, so only one x, the R squared is nothing else than the squared correlation coefficient of Pearson. That's why it's called R squared. It's a little bit more complicated if we have more than one x, more than one dependent variable, but the general idea that the R squared gives the share of variance of y which is explained via the regression line. This one always holds true. That's what's summarized in this line here. The coefficient of determination gives the share of the total variance that is explained by the regression line. So we not only learned how to determine our parameters, our coefficients of the regression line, but also how we can, by using or calculating the R-squared, the coefficient of determination, evaluate how good our regression line actually fits the data. Well, and this is a nice result. And this also wraps up all the parts I wanted to discuss in this short unit on linear regression. I hope you enjoyed it. And if you want to see more of this type of units, feel free to visit the rest of this playlist and the rest of this course in Statistics 1. I say goodbye and see you next time.